Alright, so here are the variables that we are given. We are given that k equals 1,528, mass is 1.7, and one of the heights is 0.9, and we are told to find the length. Now, you may be wondering why I'm saying the first height and not, just the height in general, because we do know that potential energy due to gravity is equal to mg, the mass times the gravitational force times the height. And what you might think is that this height, you'd plug it in right here. But that's actually not what you're meant to do. Because the way this works is you have the book falling, okay, and let's say that this is the 0.9 meters, right? Now, we have a spring right here. I know that's a great drawing, but yeah, the book is falling onto the spring, and this is the length of the spring. And since the book is falling onto the spring, that means that the length is actually included as part of the height as far as this equation goes. So that means, in reality, we do not just have mgh, we more likely have mg, and then it is, instead of h, we just have h plus l. Alright. And of course, we also have a few other equations that we have access to, such as the potential energy due to the spring force, which is of course equal to the potential energy to the spring force is equal to 1/2 kl squared. And you know what, let's just remove this diagram just to give us a bit more room, because we might need it down the line. Anyhow, so we have these two equations, but we also have a bunch of work equations. So these work equations include work is equal to F, the force, times the distance, times cosine of theta. Now in this case, cosine of theta does not matter because we actually have a 0-degree angle. So in this case, cosine of theta is equal to 1, right? Okay, so now we know that cosine of theta does not actually matter for the sake of this equation, due to the fact that cosine of theta is 1, and when you multiply 1 by anything, you basically get the same thing. Also, I'm very sorry if this is very monotone. Anyway, so we also have a few other equations, such as work is equal to the change in kinetic energy. And also my handwriting is slightly bad. I apologize for that as well. Anyway, so in this case, we also know that the change in kinetic energy is equal to the final kinetic energy minus the initial kinetic energy. I'm sorry, those are kind of running into each other. Anyway, so we also know that since there is no thermal energy in this equation, we can basically modify the one of the energy theorems, and basically we have the initial kinetic energy plus the initial potential energy. Oops, I forgot the E here. Is equal to the final kinetic energy plus the final potential energy, right? Okay, so feel free to pause, take a screenshot of, this video, And anyway, so since we know that kinetic energy is also equal to work, and we basically at this point the tricky part is, since we know we have potential energy due to gravity and we have potential energy due to the spring force. So in this case, since the book is falling onto the spring, that means the gravitational potential energy is the initial potential energy, and the spring, the potential energy due to the spring force is the final potential energy. So that means we can fill this in as the initial kinetic energy plus mgh plus L. Oh god, I'm sorry, my letters are going all over the place. Is equal to the final kinetic energy plus the potential energy due to the spring force, which is 1/2 KL squared. Oops, sorry, my camera did not quite pick that up. Anyway, so feel free to take a screenshot. I'm just quickly going to save this drawing and I will resume the recording in a blank slate. Okay, anyway, so right now we have our equations over here, which we can further reference back. Oh dear, that has become very fuzzy. Okay, there we go. Anyway, that has decided to become very fuzzy, but now you can see that all of our equations are right here. So basically now, we have to figure out how to basically connect all these equations to calculate the length. So one way we can do this is we can actually rewrite the other equation from before with the how the kinetic energy and the potential energy all link together. Basically, since we know that delta KE is equal to final minus initial, then that means we can rewrite this as so we can rewrite this as potential, the initial potential energy, which of course will be our mgh plus L, minus our final potential energy is equal to the final kinetic energy minus the initial kinetic energy. Oh yeah, feel free to go back, and if you didn't think to do so, please screenshot the formula thing, the formula sheet thing that I made. Anyway, so now that we know that, we also know that I'm just going back in and substituting the equations we had earlier, minus the spring, yeah, it was the spring potential energy, and now we know that this is equal to work because this is delta K, and you know what also is equal to work? The force times the distance. Yeah, the force times the distance. And okay, anyway, so let me not lose my train of thought again. So we also know that force is equal to the mass times the acceleration, which in this case the acceleration is 9.8, the same as gravity, due to the book falling down, and of course the mass is the same mass as the book, so therefore we now have we can basically change this equation once again And of course the distance will once again be h plus L, since that is, of course, the distance that the book is falling. And so now eventually we can basically substitute this in and substitute this in as well. Okay, this is getting very messy, I'm sorry. Anyway, so we have mg h plus L minus 1/2 k L squared. Oh dear, that's a very ugly K. And is equal to mass times gravity times the distance, which is once again h plus L. And then basically from there we can go ahead and plug our numbers in, which would give us 1.7 times 9.8 times 0.9 plus L minus 1/2 and 1,528. Pardon the dogs in the background. I'm not sure if they're coming through in the video. I'm very sorry if they're distracting, but there's not much I can do about them, unfortunately. Oh yeah, 1,528 L squared is equal to, I'm just gonna put down on another line here because my handwriting is very large, is equal to the mass once again times gravity, which is 9.8, and then it is wait, oh shit, I lost my, oh wait, no, I was here, okay, times h, which is 0.9 plus L, right? And so from there we can use our good old friend Wolfram Alpha if math is not your strong suit. Of course, if math is not your strong suit, feel free to solve it without Wolfram Alpha. But since I know that's not everyone's strong suit, I'm just going to use it for the sake of this instructional video or whatever you want to call this. Anyway, so we now have 1.7 times 9.8. Also, I'm very sorry, my hands are a little bit shaky. Oops, let's not cover the camera. 9.8 times 0.9 plus L, and yes, Wolfram Alpha does not care what you use for the variable, minus 1/2, and then of course 1,528 L squared is equal to 1.7 times 9.8, and then that is 0.9 times 0.9 plus L. Okay, and then assuming L is a variable, yes, of course it's a variable, and oh dear. Okay, guys, so I figured out my mistake. So yeah, no, do not worry about force. Do not worry about any of this work shit. Do not, no, just don't. Because, yeah. So I temporarily forgot for a brief second that, that's the change in kinetic energy, the change in kinetic energy, oh dear. Oh no. Oh dear, that's not very neat. Okay, anyway. So I briefly forgot that the change in kinetic energy is actually equal to 0. The reasoning behind this is that due to the fact that the book, when the book is dropped from rest, which means that the initial kinetic energy is equal to 0. And when the book has fallen on the spring, that is also equal to 0. Due to the fact that when the book finally lands, there's no kinetic energy due to the lack of motion. So either way, these are both 0, which means that kinetic energy is actually equal to 0, which means that we can actually simplify this whole guy down to 0. Okay, which means we do not do any of this. We do not do any of this. I'm so sorry, guys. But hey, at least, if I hadn't made this and then gone into Wolfram Alpha, I probably wouldn't have realized that I was giving y'all bad information. So hey, I mean, at least that's a plus. So anyway, none of this, none of this, none of this. Okay? This is 0. Oops. This is 0. This is also 0. And then when you plug it into, let me make sure it's the same. But yeah, basically, you plug it into Wolfram Alpha, and you should get the answer, basically. So yeah, and I hope my little blunder was not enough to kind of ruin this tutorial video, but yeah, I hope you enjoyed. I'm sorry that it's like almost 18 it's almost 20 minutes long. But yeah, okay.